My name is Forrest Glines. I am a graduate student at Michigan State University working with Philip Greta and Brian O'Shea. And this is my work studying magnetized decaying turbulence in the Taylor-Green vortex. Decaying turbulence refers to turbulence that decays from a large-scale perturbation instead of being driven by an external driving force. For example, a galaxy cluster merger, as shown here, would cause decaying turbulence in the intracluster medium. We're also focused on magnetized turbulence as opposed to hydrodynamical turbulence. In a purely hydrodynamical flow, energy transfers to smaller and local, or similar, length scales. So large eddies break up into slightly smaller eddies. This leads to the turbulent cascade, as described by the Kolmogorov theory of turbulence, and has a k to the minus 5/3 scaling in the power spectrum of the kinetic energy. In a magnetized plasma, because magnetic field loops can be compressed, convected, folded back onto each other, and break up through magnetic reconnection, energy transfer is not strictly downscale and local. Energy can be transported from small scales to large scales, which is known as inverse energy transfer, or between very different energy scales, which we call non-local energy transfer. These additional modes of energy transfer in magnetized turbulence can lead to a departure from the k to the minus 5/3 power spectrum in hydrodynamical turbulence. To probe magnetized decaying turbulence, we simulated the magnetized Taylor-Green vortex, where an initial large-scale vortex decays into turbulence without an external driving force. Here we show the Mach number on the left and the magnetic pressure on the right after less than a dynamical time in one simulation and after 5 dynamical times in the same simulation. We explored the behavior of the turbulence using different initial Mach numbers and ratios of kinetic to magnetic energy. Generally, we found that the magnetized decaying turbulence does behave differently than hydrodynamical turbulence. To highlight one result, the spectral indices of both the kinetic and magnetic energies do not follow k to the minus 5/3, but evolve as the turbulence develops and can depend on the initial ratio of kinetic to magnetic energy. For example, here we show the spectral index over time from 3 simulations, where the initial kinetic energy is equal to the magnetic energy on the left, where the initial kinetic energy is 10 times more than the magnetic energy in the middle, and 100 times more kinetic energy on the right. When the initial magnetic energy was weak, the spectral index after several dynamical times was flatter, reaching a k to the minus 4/3 scaling. And that's just one result. Among other things, we also saw that magnetic energy tends to dominate over kinetic energy after a few dynamical times, even if the initial magnetic energy is weak. We also do an energy transfer analysis, where we examine how energy transfers between and within the kinetic and magnetic energy reservoirs. Through that analysis, we also saw temporary inverse energy transfer within the kinetic and magnetic energy, and also significant non-local energy transfer from large-scale kinetic energy to small-scale magnetic energy. This non-local energy transfer was especially apparent when the initial magnetic field was weak, and so this transfer might explain the k to the minus 4/3 spectral indices. Please check out our paper on arXiv and feel free to email us any questions.